now let's talk some more about SPI. And what we kind of left off with last time is that we had tied the F28379D processor with its SPI B peripheral. It just happened to be the one we chose. There's an A, B, and C. I have the A and C SPIs wired to other devices for possible use. They're actually not soldered on right now, but anyway. And we found that not only is this SPI B connected to this MPU 9250, our IMU. This is another IMU. So this has got 3 axes of acceleration. There we go. 3 axes of gyro, and actually a magnetometer on there too. We're not going to deal with the magnetometer. That's something you could possibly play with in the final project if you'd like. But let's just think of it right now. That's got 3 axes of acceleration and 3 axes of gyro. And we're going to get to this today. We need to start talking about this MPU 9250. But before that, I want to continue just to kind of I want to talk to you about another chip just so you get this idea of how do we look at the data sheet and figure out what we need to send over to the device and then how we send that over to the device. So we actually don't have them soldered, but on the green board of the robot, there is 4 chips actually that just aren't soldered, LS7366 chips. And this would allow, if I needed to in the future, to add more optical encoder channels. Okay, right now we have a way to plug in 3 optical encoder channels, and those are sensed by the 28379D processor's EQEPs, right? Remember the EQEPs that we played with in lab 3, and now you're going to do it again in lab 5. Well, this, so their job, they have the A and B signals from an optical encoder coming into them, and these LS7366 chips, their job is to count the number of pulses, right? The number of counts per revolution of just the number of counts that an encoder has moved, right? And we know that we know that there's X number of counts per 1 revolution, depending on what optical encoder you have it plugged into. So anyway, our job is what we need to figure out here in this lecture is how to read the 32-bit count from this register, okay? From this chip, actually. Now, it's a register on the chip. And so, again, this LS7366 chip is not something we're actually going to use on the robot, okay? Unless we come up with some project needing an extra optical encoder, we could solder one of these chips on. There's a spot for it on the green board is what I'm saying. But anyway, but we're just going to go through this. How can we communicate through SPI over to this chip? Then when we're done with that, then we'll get into the MPU 9250. Okay? That's where we're going. All right. So again, we have on these chips the master out, slave in, master in, slave out, S clock, and slave select or chip select, whatever they call it. And then here, same thing, master in, slave out, S clock, and slave select. And especially if you've done exercise 3 of the homework, you know that we have the GPIOs 63, 64, 65. I don't remember the exact order, but one of these is master out, slave in, one is master in, slave out, and one is S clock. I don't remember the exact order of these, so it could be different, but those 3 produce those 3 signals. And master in, slave out, and then finally S clock. And these, again, are just daisy chained to those pins. Master in, and that's how we wire it. Okay? And so to get data over to this chip, we need to write to this register in the SPIB called the transmit buffer. Ah, shucks, buff. Now let's erase that. Draw. TX buff. It's called SPIB TX buff. So we have to write to that sucker, all right? And that's how we get data across the serial port lines. That's the only way to get data across those serial port lines, is to write to this register inside the SPIB peripheral of our F28379D. At the same time we're transmitting, we are also always receiving. I've said that a million times, haven't I? Well, not a million. Transmitting and receiving at the same time. And so when we're done transmitting, we are also done receiving. And so our data goes out in this register, the TX buff. It comes in SPIB RX buff. Okay? So, yeah, hard to, but so the data now coming across, that's coming back to us on the master in slave out pin, right? Remember, these have directions. The master out is always in this direction, going towards the slave, driving data to the slave. The master in pin is always coming from the slave to the master, and then the master always produces the clock. Okay? All right. And so these are our registers that we need to deal with to get data back and forth. Okay. Now, what do we do in our initializations, in the inits? We'll come back to that picture. What's the main things we're doing with the init of SPIB? Well, there's a couple things, right? We need to set the mode. Remember, there was 4 modes, wasn't there? The 00 mode, 01, 10, or 11 mode. We find that out by the data sheet, okay? And you'll figure that out for the MPU 9250. Figure out what mode it needs to be in, or the lab gives it. I can't remember. But anyway, we'll do that mode. Then the other thing we need to set up is the bit rate. How fast, how many bits per second in other words, what is the frequency of this clock signal? Okay? Not all chips can go super fast. Okay? And sometimes the faster you go, the more issues you have with noise, possibly. Other issues are just that the device out there is not fast enough and all this kind of stuff. So what we ask you on this one, the MPU is not, M9250 isn't a super fast chip. But we can communicate with it at 1 megabits per second. We probably can go a little faster than that, but we don't really need to. So that's why you're asked in these homework problems to set up the bit rate at 1 million, right? 1 million bits per second. Okay, so that's one thing we have to set up. And there's a register, the BRR, I think it is, or BBR, whatever it is, baud rate register that allows you to set up this bit rate. So that's something else we have to set. So this, 2. Then what we're going to get in today and really talk about is the Fifo. There is an output Fifo. So I'll call it the transmit Fifo. And there is a receive Fifo. Okay? And then really what there is kind of this SPI DAT register in between these. Data register. Okay? We are setting up, another thing we have to initialize is this Fifo. How do we want to use this Fifo? Okay? What you're going to see for this little example I'm doing with the LS7366, every one of these elements, and by the way, there's 16 elements on the Fifo. Okay? So boom, 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 you can fill up to 16 things. This is not exactly 16 here. You can fill up to 16 things on this FIFO. Same with the receive FIFO. You can fill up as much as, you don't have to fill it all the way up to 16, but you have that capability. Okay? There is a register that we need to set up, and when we have to think about which is the best way to do this, there is a register called part of a register called SPI char. Okay. This indicates how many bits, really, when we do a write to this FIFO, how many of those bits that we write get shifted out. Okay? But what would make the most sense is if you can figure out how to do 16 bits all the time. That seems like the most optimal. But as you'll see, as I talk you through it with this LS7366, it's going to be a little easier to talk to these chips by only sending out 8 of the bits at a time. So in other words, when you write to the FIFO and we set SPI char equal to 7, it's a 1 minus the number of bits. So when you set SPI char equal to 7, that means each element on the FIFO, we're going to ignore the upper 8 bits and only shift out the bottom 8 bits. Okay? I'm getting to it. I know we got to explain what does that mean, the shifting out and all this kind of stuff. But that's what that SPI char is setting up. Okay? And now if we would, when we get to the MPU 9250, we're going to change that, and you're going to see in the homework, it asks you to put SPI char to 16 bits. Okay? And that's what we're going to use for our actual homework. But for this example, I'm going to show you that, well, you can make it work with 16 bits, but you would have to, yeah, anyway. It's a little bit easier to think about if we do this one with 8 bits. Okay? All right, so we set that up. And let's see, the final thing we need to set up is the interrupt. Okay? And what I'm going to try to show you today is that it's much better to use, well, it's much easier to think of and use if you use the receive SPI interrupt, the RX interrupt, compared to the transmit interrupt. Okay, there's both. There's an interrupt that occurs when we have received X number of things on the FIFO. So you can set it up when 3 things are sitting in the FIFO ready for you to read, interrupt. You can do that. You can do when 7 things are sitting there, right? 7, in this case, with SPI char equal to 7, that would mean 7 8-bit values are sitting in the FIFO. And boom, we can get an interrupt. And then we go read all those 7 values. Okay? The transmit interrupt's a little different. The transmit interrupt is when the FIFO is empty, not when the transmit is fully complete happening. So we'll come back to that just anyway. So we're going to find that because we have to pull the chip select high and low manually, it'll be better for us to use the RX interrupt all the time instead of the transmit interrupt. Why? Because we're transmitting and receiving, right? If the receive interrupt happens, that means we've received 3 things, for example, if we set the interrupt for 3 things. Because we're transmitting and receiving at the same time, that interrupt also says that the transmit is finished, right? If we've received data, the transmission is definitely done too, because we're receiving and transmitting at the same time. Good. So, yeah. Anyway, so you could also think of this RX interrupt as a transmit complete interrupt too. All right. Good. So, we've got all this set up now. Now we want to get data over to our device. Okay? And what we, again, did last time, let's get those data sheets up. And right here, I'm going to go to, and again, don't feel like you have to understand this exactly what I'm talking about. Yes, this is confusing, the registers. The most important thing I want you to understand here, you're going to have to understand it better for the MPU 9250. But for this chip, again, we're just figuring out, all right, how do I communicate with this chip? And last time, what we did is we said we need to set up the MDR0 register. Remember that? Okay, so this MDR register, we want to set it up in ×4 quadrature mode and this filter clock divisor by 2. Okay? Everything else is zeros for this. Free running clock and all this kind of stuff. All right, and so from last time we found, well, if I want to put this in quadrature mode, then these 2 bits need to be 1, don't they? Oh, sorry, the wrong place, isn't it? I can just write, very good. So we want this, that's bits 0 and 1. So these guys need to be 1, 1. Agree with that? Okay, that's what we want to send over. We want to put it in free running mode. So those are 0, 0. We want to disable the index, 0, 0. And then finally, we want to do, fine, we'll do positive index or negative index. It doesn't really matter. Leave that 0. We're not using the index. That's why it doesn't matter. And then we're going to put the filter clock divisor to 2. Okay? All right, and that filter clock gets rid of the little noise glitches and all that kind of stuff as best it can. So we want to send to this register the hex number 83. Agree with that? Okay, so that's what we're going to send. Now the way to send that is, the way it handles this is the first 8 bits you send over, you must write those 8 bits. They're put into what's called the instruction register right here. Okay? And so what we want to do is we want to write to MDR0. Well, we look here. The lower bits are all 0, or well, don't care. So we're going to write 0 out to those bits. Okay? The next 3 bits are that we want to write to MDR0. Okay? So MDR0 bit 3, that'd be 0, 1, 0, 0, this order. All right? See what I'm doing right here? This is what we'd write to the instruction register. And what instruction do we want to do? We want to do write. So these last bits are 1, 0, 0, 1, or however you want to say it. Okay? So this is the number hex 88. So what we need to do, if we want to set up the MDR0 register of this device to hex 83, we are going to have to send first, we're going to have to first send hex 88 over to this device. That's telling this device, hey, the next 8 bits that are coming, you need to put those into MDR0. Okay? And so it knows that. If for some reason you would stop and not send the next 8 bits, then the device would just say, well, it cancels the command. But in our case, we're going to send both of those, OX88, and then we're going to send hex 83. Okay? So, great. Great, Dan. Maybe you don't even, Dan, I'm a little confused on this right now. What is that? Why is it those bits or whatever? For now, don't worry about that. Just know, okay, we need to send over 88 and 83. All right, so what do we do in our C code? Well, we have 2 places where we put our SPI code. We have the initializations of the device. Okay, so we need to initialize this once, right? Usually the initializations only happen once for the device, once you power on and you talk to the chip once. Those initializations, great place to put them is in main. Okay? And remember, when we're doing all our initializations in main, we're putting them all before the, you're getting a good sleep back there, Alp, huh? You're relaxed, buddy. You should have brought a pillow. We put all those initializations for the everything above our enabling of interrupts is what I'm trying to spit out. Remember that? So we want to write our initializations such that no interrupts are being used. Okay? So, and before we enable it, because this is only happening once, we really don't care that it takes a little extra time to run these initializations. Because remember, using interrupts is the optimal way to do things. Other things can be running, and we wait until that interrupt happens, and then we process on that chip, right? But in main, it's only happening once, and we're doing all those initializations. So, in other words, what we need to do is in main, we need to send the data out, and then in a while loop, wait for that data to be transferred over to the chip. And then when it has finally been transmitted, then be done. So you'll see us in main send out data, sit in a while loop, wait for it to be done, then read the data after that. Okay? So that's what I want to do first. Because this is an initialization, we only need to send this data over once to set up the chip. Let's put this code in main. And so what would we do? We go down here. What you're going to see, and I give you a lot of this in the, not this for this chip, but for the MPU 9250, I give you a lot of these initializations. And so here we go. And we started this last time, but I found out it's actually one of the LS73 chips, 66 chips, is GPIO 25. So the first thing we want to do, right? So back to our drawing here, we need to select the chip that we want to talk to. And so it happens to be that GPIO 66 is wired to slave select of our MPU 9250. The GPIO 25 happens to be connected to the slave select of one of our LS7366 chips. Okay? So, in order to talk to this guy, we need to pull GPIO 25 low. Okay, so up in main, in my code composer, where am I at? Right here. Okay, so that's what I do. I'm ready to talk to this guy, so I clear chip select. Okay, once I've cleared chip select, then I'm ready to talk to the device. And notice, how do I send out that 88? And remember, up in the initializations, somewhere I set SPI, the SPI char bits. For this example, I set to 7, which means it's going to send 8 bits out at a time. Each element that I put on the FIFO, we're only going to send out 8 of those bits. Because this transmit FIFO buffer, each element is 16 bits long, okay? But we're saying only transmit out the bottom 8, okay? So we're writing to it the first element on the FIFO, 88, the next element on the FIFO, 83. So what happens there? With our picture again, what in the FIFO, when we do that, what happens is, let's erase that, draw. When I do that command, and I got my elements, what happens is hex 88 gets put into this element on the FIFO, and I wrote right away, I just boom, boom, didn't I? I wrote 2 times in a row and did not wait for the data to actually get across, did I? That's because I have a FIFO. If I didn't have to FIFO, I'd be able to write one thing and wait till it's done transmitting, and then write another thing. Now, if I had to write 20 things across, I'd be in trouble, wouldn't I? Because I couldn't write 20 things, boom, 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 into the FIFO, because it would overflow the FIFO, wouldn't it? There's only 16 elements on the FIFO. Well, good news. In this case, all I needed to write was 2 things, didn't I? So I could write hex 88, and then hex 83 gets put on the next place in the FIFO. Okay? All right. Hold on. Yeah, but what happens now once they get put on the FIFO? Let's think now here first. So we go back to the code. All right. So we've just pulled chip select low, and SPIB, we shoved out hex 88 first, and then hex 83. Good. Now what we've got to do is we've got to wait. And I'm going to go to your lab and get, just so I don't have to type the code in, but you'll see here in some of the initializations I give you for the MPU 9250 down here. This is for exercise 5, so this is due after spring break. But anyway, you can keep on working on it. see what I do? Let's just look at an example here. I pull chip select low, and then I write out something to the transmit buffer, and then look, I sit here and while loop. Okay, this is one, I just want to copy this so you see this. Control C, and then we'll go back to here in our code composer. Now what we've got to do is we've got to wait. Okay, what are we waiting for? We're waiting for, what this says is this, the receive Fifo status is what ST stands for. Because we're sending out 2 values on the Fifo, how many values are we going to receive under the receive Fifo? 2, right? Simple. So what we have to do here is we've got to wait for the receive Fifo status to be equal, not equal to 2. When it is equal to 2, we know we've gotten 2 things. And because we're transmitting and receiving at the same time, we know also that our transmission is finished too. Agree with that? Okay. So again, because we need to do this while loop, because we're not using interrupts yet. Okay. Then when we're done waiting, so in other words, we sit there and wait. The SPI starts shifting out the bits. Okay, one at a time, bip, 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 at our 1 megabits per second rate. Okay, when that's done, we've got our 2 values sitting in the receive Fifo, and so we also are done transmitting, so we need to set the chip select back high. Agree with that? So we select the chip, and then we shove those values into the Fifo, and then what happens is the Fifo actually sends its value over to the SPI serial port, and 1 bit at a time it's going across the data line, out the master outline, the things you're transmitting. And at the same time, we're reading in data from the chip out there, from the LS7366. Now, what we need to know is that data we get back, is it important at all? Well, in this case, it's not. If we go look at the data sheet again, let's find it. Here we go. If we go down to our timing diagrams here, okay, so we're doing a command similar to, which one here? Yeah, this guy right here. This is writing to, I think, MDR1. Yeah, this is a command for writing to MDR1. But it's the same thing, just a little, the bits in front there are a little different. But we write out data to MDR0. Look at what the data sheet has for what's coming back on the master in pin. It's just kind of, they put it here as just high or low, right in the middle, which it can't be, right? The data line can't be just right in the middle. It's either high or low. And what I would call that is that's garbage data coming back. Nothing. Okay? But what we are going to find that we've got to do in our code, notice we're going to now, next thing we're going to do is we're going to talk Control C, we're going to talk to Control V, MDR1 we need to set up, right? The first one was MDR0, the next one is MDR1, and we'll find, we won't go through this with Control I, we'll find that what we, just trust me, what you need to send over is hex 90 and then 00 is what you want to set up MDR1 to, okay? And we would do the same thing. Pull chip select back low, send over 2 more bytes. It's actually kind of interesting. Is this necessary? Notice we clear the slave select, send our data, and then we set the slave select, and then clear it right away again. What do you think? Would that be necessary? It actually is, because that high going edge of chip select tells the chip, hey, I'm done with this command, look for the next command. Okay? So you do have to pull that chip select high, and if it's okay, you can pull it right back low again and send out the next command. So this chip select low and then high tells the chip when the command is done. Okay? All right. So that's important. But notice, if I would leave the code like this, FIFO status 2 means that two garbage values are sitting here. So garbage and garbage, just meaning they have no data that we're interested in. Okay? That's what I mean by garbage. So if I go to these next lines of code and send out 90 and 00, what would I have to while loop here to wait for in order that we wait till the transmission's done? Somebody else in Mario School, what do you guys think? How many things are on the FIFO already from the first command? 2. So we shove 2 more things into the transmit. How many more? 2 more is going to be on that FIFO. We'd have to wait for 4. And then if we had to do another command, we would finally get to a point where we filled up the receive FIFO, all 16 of them, wouldn't we? So what we want to do, every time, even if it's garbage data, we have to read it off the FIFO. Okay? And to read it off the FIFO, you simply say SPI regs dot SPI RX buff. Oh, I'm sorry, you got to read it. So that's the end. We would just say some dummy variable, dummy or whatever you want to call it, equals. See what I did there? And by just calling that once, I have pulled the bottom value, the bottom garbage value off the FIFO. And then this guy plunks down to the bottom element of the FIFO. Okay? And so your only window into this receive FIFO is this SPI BRX buff. That's your only window to read the FIFO. The only window to transmit into the FIFO is SPI transmit buff, is the name of the register. Okay, we can't directly talk to the receive FIFO, transmit FIFO, or the receive. The only way is through this guy. So it clunks down, and then we do one more read right here. You can use the same variable, and copy this line of code. Control C, and do it again. Same exact line of code. Okay, that pulls, boom, boom, both those values off the FIFO. Okay, good, great. And so that's done. We have by doing those lines of code right there, we've transmitted 88 and 83 over to our device, and it set it up the way we got. Now we have it working with ×4 counting. Okay, the quadrature decoding, and then of course the next one, same thing. And we would, of course, do the same. When we're sending that over, we're getting no data back. Control C. Oops. And we'd put R2 right here. Control V. Okay? Yes?
Why are we sending those values into the dummy variable? Like, is there no other way of getting it?
Correct.
Or do we need them for later?
You do not need those for later.
So
that's why I call it dummy. It's something that gets it off the FIFO. Yeah. That read instruction needs to happen. Okay. Well, okay, one other way you could do it is just you could reset the FIFO. And I don't know, there may need to be a little bit of delay after you do that because of the clocking and all this. So this is the fastest way to do it. Another way to do it, there's a command to say reset FIFO. And that would clear the FIFO totally. But I think this is a better way to do it. So, okay. Good. All right. Now, great. We've got this chip all set up, ready to go, and it's counting that 32-bit count. What we need to do now is every millisecond, right? It's our feedback. It's an angle of something, right? Every millisecond, we want to go and read this now, okay? And remember, every millisecond, a lot of things are happening on this chip, aren't they? Okay? So now we want to use the interrupt capability of the SPI. And so what we do is we have our receive interrupt. Like right here, just so SPI B ISR. You set it up just like we've been setting up all the other interrupts. Okay? And so what do? In a timer or in your ADC interrupt, you will initiate the command to talk to this device. Okay? And actually, running out of time, so I don't want to get into all the specifics, but let's go to the timer. What we need to do is the following. For this LS7366 chip, get the right code, just so if you do double check me, I got the right thing. Yes. So, oh yeah, interesting. I'm not going to get to this, but anyway, I forgot one little minor point here, but that's okay. There's some bit shifting that needs to be done, but we're not going to worry about this for the example because we're going to be sending the full 16 bits when we get to the MPU 9250. Okay? So I actually did forget one thing in this initialization, and because the bits are sent over most significant bit first, where did I lose it? Actually, you need to left shift this 90 by 8. So anyway, that's the appropriate way. Anyway, for that device, let's not worry about that though. The idea is we needed to get that data across to the device. Okay, so what would we do inside our timer? Control C. We're going to go down here and let's put it in timer 0. Let's say this is happening every millisecond. And what are we going to do? Well, what we need to send across in order to start to read the count value of the device, we need to send over the command E8. Again, we would look at that instruction register and figure out what bits need to be high and low. To read the count is hex E8. Then we need to just send over, what we need to do is once you've sent over E8, then the next 4 8-bit values that come across is your 32-bit count. Okay? And so we send over E8, then we send over something so that we're getting back data, something again. That something is anything you want it to be. Okay? So in this way, and that's shown in the data sheet. Let's just get it here. What we're going to do is actually send in, let's just copy it. Again, now this is just for this chip. You're going to do a little bit different things for the MPU 9250. So all we have to do in the timer is clear our chip select. That selects our SPI device. Then we write what we need to send over to the transmit FIFO, and we're done for now. Except for one last thing, and that is to set what's called the RX FIFO. So let's see, SPI B regs dot, what is it? SPI RX, am I going to find this quick? RXX dot bit dot, hey, I did good. This thing called RX FIFO interrupt level. Okay? What this is saying, remember I had to say we could get an interrupt when a certain number of bytes is sitting, or a certain number of words is sitting in the FIFO? We just sent out 5 things. We set this equal to 5, and so before we run that, the FIFO interrupt level, or the number of items on the FIFO, the received FIFO is 0. Nothing's been received yet. But we go and shove 5 things into the transmit FIFO. That means when the transmission and the reception is complete for this data set, for this read of the device, the number of things on the FIFO will be 5, right? We send out 5, we're going to get back 5. Agree with that? So what we're waiting for is 5 things to be on the receive FIFO, and that's what that means, the RX FIFO interrupt level. So we set that to 5. Then when you get the interrupt, 5 things are sitting on the receive FIFO. That means you're inside your interrupt routine, which I put up here. And so what we need to read is the RX buff. Dot SPI RX buff. There we go. And we read that once. Dot SPI RX buff. We read it how many times? 5 times, because we had 5 things in the receive FIFO. So let's cut this, Control End. Oops, Control Z. And End, and there we go. And so we're going to read this 5 times. Now these variables, SPI value, we could create more of them, right? We could make value 1, value 2, value 3, value 4, or however you want to do it. These are all just 16-bit integers. 3, 4, 5. Okay? Well, what happens here, and look, I'm reading that from that same register. So I'm pulling off those 5 things. When I'm done, somewhere here, I've got to set the GPIO data regs dot GPA set dot bit dot GPIO 25, right? We got to set that pin too, don't we? That disconnects, that stops our communication with the chip. But now, okay, great. I've read those 5 things. I pulled chip select high. Well, the good news is in those 5 things, 4 of them is actually your data, right? 4 of them is, you put, they're each 8-bit values. We've got to put the 4 together to make a 32-bit value. Because what are we reading? We're reading a 32-bit value from that device. If we go to the data sheet again and look down here, they just, for space on the paper, they did it this way. So look what they did here. See, this is the command, the E8 that we just sent over. Okay, let's see. Sorry, that's in our code here. So we sent over in the timer, remember, right here, E8. Where did it go? Hold on 1 second. Let's just get down to the timer here. Right here, we sent over this hex E8. Okay, that was the command to read. And then we send anything, garbage, whatever you want to send. Okay, and then look back here in the PDF, right? So we sent over something of importance. What do we read back when we're sending that over? Nothing. Garbage. But when we send random data, or zeros like we did, we first get back byte 1 and then byte 2. In our case, this is just doing 16-bit a read. We are reading 32 bits. Okay, so 32, the bottom 32 bits there would be valid. We read all those into our ISR, interrupt service routine, and chunk it back together into our 32-bit count. And now we know we have the reading from our optical encoder chip. Okay? All right. Well, we'll summarize that real quick in my recorded lecture on Wednesday, and then I'll get heavy into the MPU 9250.